In the last lecture, I defined the covariant derivative of a vector field. So a vector field V, the covariant derivative del alpha V mu, is defined by partial alpha V mu plus gamma alpha beta mu V beta. And these gammas are the Christoffel symbols. They're defined by gamma alpha beta mu equals 1/2 G mu nu times partial alpha G beta nu plus partial beta G alpha nu minus partial nu G alpha beta. Let me remind you that the G's with the lower indices, these are the components of the metric. So the metric itself is an operator that has two slots to insert two vectors. And the G mu nus are just the components of that operator. G with the upper indices, this is the inverse of G with the lower indices. And also remember the partial symbol here is just shorthand notation for the derivative with respect to the coordinates. The covariant derivative itself, what this is, it's actually the muth component. So del alpha V mu is the muth component of the derivative of a vector field V along the x alpha coordinate line. And the derivative is defined by parallel transport. So the picture we have is, here's the x alpha coordinate line, and we have a vector field, so there's a vector defined at each point along this line. And if we want the vector, the derivative of the vector at a point, say P, this point here, what we do is we look at the vector at a nearby point Q, and we parallel transport that vector. We keep it parallel to itself and don't change its angle as defined by the metric. So here's the parallel transported version of the vector at Q, and then we subtract those two vectors. Recall the original notation that we had for this was dv dx alpha parenthesis mu, meaning we differentiate the vector field V by parallel transport along the coordinate line x alpha, and that's a vector, and we're looking at the muth component of that vector. Now, what if we want to differentiate a vector field along some other curve that's not a coordinate line? So, for example, let's take a curve x mu of lambda, parameterized by some parameter lambda. The vector field is defined all along this curve. Given this curve, we can define a derivative operator d by d lambda, and this is sometimes referred to as the tangent vector to this curve. Tangent vector to the curve. Now, expanding this using the chain rule, this is partial x alpha partial lambda d by dx alpha. So written this way, I've written this vector, this derivative operator, as a linear combination of basis vectors, and the coefficients here are, of course, the components. So these coefficients are the components of this tangent vector. The vector that I'm just denoting here by d lambda. All right, so if we want to covariantly differentiate this vector field along the direction lambda, all we need to do is take the linear combination of derivatives along the coordinate lines given by this expression. So in other words, using this old notation, we would write dv d lambda muth component is equal to partial x alpha with respect to lambda, so the same coefficients here in the linear combination, times dv dx alpha muth component. So you'll notice what's being asserted here is that the covariant derivative along this direction is the same as, well, let's say this is the x0 direction, this is the x1 direction. What we're saying is that we can differentiate this vector field along this curve lambda, x of lambda, by parallel transporting this vector back to here, or alternatively by parallel transporting the vector along the coordinate lines like this and then like this. So what we're asserting here is that this vector parallel transported from here to here is the same whether we transport it along this curve or along the two legs of this triangle. And it's not true that the parallel transported vectors will be exactly the same, but it turns out that the difference between transporting this vector along these two different paths differs by higher order terms, that when we think of this as a limit of the, taking the limit as we parallel transport, subtract the vectors, and divide by delta lambda, in that limit the difference goes away. And we'll see that more clearly later in the course when we define the Riemann curvature. Of course, this factor is just what we write in more standard notation as del alpha v mu. And these coefficients are just the components of the tangent vector d by d lambda. And in fact, let me invent a little simpler notation for this. Let's let t stand for the tangent vector, so it's just another notation for d by d lambda. Then the components of t are partial x mu with respect to lambda. And so we can now write this as the covariant derivative of v along the curve given by x of lambda. The muth component is t alpha del alpha v mu. Now in deriving this expression, we only require v and t to be defined along the curve x of lambda. So for example, here's the vector field t, or v rather, defined all along this curve. Let's say this is the tangent vector along the curve t. This is v. But of course, it's often the case that vector fields are defined everywhere in space or space-time. So we can consider a vector field that's defined elsewhere, not just along this curve. And similarly, we can consider this vector field t could be defined everywhere in space or space-time. After all, if you think about it, here's a general vector field. Any vector field can be considered as the tangent vectors to a set of curves that are the integral curves of the vector field. So these are the integral curves. Integral curves of some vector field t. And the way we define the integral curves given a vector field t is we just define them by the component relation. So given t everywhere, we can integrate this equation for x mu of lambda. And whether that gives us this curve or this curve or this curve depends on what initial conditions we use for that integration. All right, so we can read this expression more generally as vector field defined everywhere on space or space-time, T alpha, del alpha, acting on a vector field that's defined everywhere in space or space-time. So T alpha, del alpha, mu are the components of a vector. T alpha, del alpha, v mu are the components of the vector, which we can write in terms of a coordinate basis as T alpha, del alpha, v mu, d by dx mu. Now there's another way we can look at this. We can consider del alpha v mu to be the components of an operator that acts on vectors like the vector t, or vector fields, to give a vector like this vector field here. In other words, this idea of an operator acting on a vector, we've encountered that before when we talked about covectors. Covectors act on vectors, and we can expand a general covector W as a linear combination of basis covectors dx mu. So this object is the components of the following operator, del alpha v mu dx alpha d by dx mu. All right, so here we have one piece of this expression that acts on vectors, and when it acts on a vector, what we're left with is some components and a vector. Now this notation is a little bit misleading because when you look at this, you might mistakenly think that this covector is acting on this vector, and we want to make sure that's it's clear that this covector is not acting on this vector. So people usually put a little symbol in here called the outer product, which is a little times symbol with a circle around it. So this symbol means the outer product. Okay, so again, the way we read this is this operator accepts a vector like the vector t, and it gives a vector. So let's do that explicitly. Let's let this operator act on a vector t. So the vector goes into this slot. So we have del alpha v mu dx alpha acting on t. And then we're left with d by dx mu. And now this covector acting on t just gives the components of the vector. So that's t alpha. And now we don't need this symbol, this outer product symbol anymore. And of course we can just rearrange factors to make it look like what we had previously, T alpha, del alpha, v mu, d by dx mu. So this operator acted on a vector t to give a vector given by this expression. We've spent a lot of time in this lecture and previous lectures talking about some rather abstract mathematics. So let's take a step back and consider why we're doing this. Remember that we need to be able to describe physics in a curved space-time. And in curved spaces and curved space-times, we don't have any nice set of preferred coordinates to use. In fact, one person could use one set of coordinates, another person could use a different set of coordinates, but the physics that they describe should be the same, so it should be independent of the coordinates you choose. And that's why we need to develop this language and this mathematical machinery. So let me give you an example. This example uses flat 2D space, which of course does have a preferred coordinate system, namely Cartesian coordinates, but we can consider other coordinate systems like polar coordinates. So let's start with Cartesian coordinates. x and y. And let's consider a vector field. The vector field is y d by dx minus x d by dy. And what I want to do is compute the covariant derivative. And then we'll go back and we'll redo the calculation using polar coordinates and see that we get precisely the same thing. All right, so what is the covariant derivative? It's the ordinary derivative, partial mu, partial alpha v mu, plus Christoffel symbols, gamma, alpha, beta, mu, v beta. And here v mu are the components of this vector field. The components are, well, the x component or the 1 component is y, and the y component or the 2 component is minus x. Now, what I think I'll do in this example is what is common practice of, instead of using 1s and 2s here, I'll use x's and y's. So I'll denote the first component of v as vx and the second component as vy. So in either notation, it means the obvious thing. The x1 coordinate is x and the x2 coordinate is y. Now, for the Christoffel symbols, remember they're defined in terms of derivatives of the metric. So in flat 2D space, what is the metric? The metric is just dx squared plus dy squared. That means that the metric coefficients or components are 1, 0, 0, 1. That's the coefficient of dx squared. There's the coefficient of dy squared, and there are no cross terms, dx to dy. All right, so the Christoffel symbols, I'll remind you of the definition. It's the inverse metric, g upper mu nu, partial alpha, g beta nu, plus partial beta, g alpha nu, minus partial nu, g alpha beta. So every one of these terms has a derivative of the metric components in it, and the metric components are all constants. So all of these are 0. In fact, that's why Cartesian coordinates are so nice, is because the Christoffel symbols vanish. So in this example, del alpha v mu is just the partial derivatives of v mu with respect to x alpha. So we can now compute explicitly del x vx, that's the xx component of this. It's the same as partial x vx, but vx is y, so this is equal to 0. Del y vx is same as partial y of vx, that's equal to 1. And del x vy is equal to minus 1, del y vy is equal to 0. All right, so this, remember these are the components of an operator that takes a vector and produces a vector. So it can be written this way in terms of a coordinate basis. And as always, we're summing over repeated indices mu and alpha here. So the only non-zero components are the yx and xy. So this is when alpha is equal to y and mu is equal to x, we have 1 times dy outer product d by dx. And when alpha is equal to x and mu is equal to y, we have minus 1 times dx outer product with d by dy. So there's our result for the covariant derivative. Our covariant derivative of this vector field. Now let's repeat this calculation in polar coordinates. All right, in polar coordinates, remember the metric or the line element is dr squared plus r squared d theta squared. So the components of the metric are 1, 0, 0, and r squared. And I'm going to let r is the x1 coordinate, theta is the x2 coordinate, but for our vectors I'll use superscripts r and theta instead of 1 and 2. All right, so the first thing we need to compute is what the vector is in polar coordinates. So here's the vector, y d by dx minus x d by dy. All right, so this is y, but y is r sine theta, and d by dx is dr by dx, which is cosine theta, plus d theta by dx, d by d theta. D theta by dx is minus sine theta over r. Right, minus x. X is r cosine theta, and d by dy is sine theta d by dr plus cosine theta over r d by d theta. All right, if we now simplify this, notice we have r sine theta cosine theta and minus r cosine sine. So these terms cancel. And for our d by d theta terms, we have sine squared, an overall minus sign here, the r's cancel. We have a minus sign here as well, the r's cancel, and we have cosine squared. So this is simply equal to minus d by d theta. All right, so in terms of components, we have our r component is 0 and our theta component is minus 1. Now let's compute the covariant derivative of this vector field. We have del alpha v mu is partial alpha v mu plus Christoffel symbols gamma alpha beta mu v beta. Now in this case, these components are constants, so that means all of these derivatives vanish because v mu are constants. But we have to work a little bit harder to compute the Christoffel symbols in this case. So let's take a look. We have gamma mu alpha beta is 1/2 g mu nu partial alpha g beta nu plus partial beta g alpha nu minus partial nu g alpha beta. The metric, these components, remember, are 1, 0, 0, and r squared. The inverse metric, that's just the inverse of this in the matrix sense, so it's easy to invert a matrix that's diagonal. We just invert the diagonal entries. So it's 1, 0, 0, and 1 over r squared. Let's just compute. Let's, for example, look at this component, this Christoffel symbol, gamma r, r, r. What is it? It's g, r, and then we have this repeated index nu that's going to be summed over, so I'll leave it alone for the moment. This is partial r, gr nu, plus partial r, gr nu, minus partial nu, grr. Okay, so now grr is just 1, so the derivative of 1 has to be 0, so this term just gives 0. And similarly, we have a gr nu here. It doesn't matter with r, whether nu is r or theta. This is constant, so these give 0 as well. So this component, the Christoffel symbols, is 0. Let's look at gamma r theta theta. This is 1/2 gr nu partial theta g theta nu. I'm just inserting theta for alpha and beta here, plus partial theta g theta nu minus partial nu g theta theta. All right, now in this case, notice that we're summing over nu, so nu takes on values r and then theta, but g is diagonal, g inverse is diagonal, so the only term in the sum over nu that survives is the term when nu is equal to r. So we can set nu equal to r here, here, everywhere. But g theta r is 0, so these terms are 0. The only term that survives is this one. G theta theta, remember, is r squared. All right, so this is 1/2 g upper RR, which is 1, times minus the partial of r acting on r squared. Partial of r on r squared is 2r. The 2 cancels here, and we're left with minus r. All right, I'll leave it up to you to compute the rest of the Christoffel symbols. Gamma theta, r theta. Remember, the Christoffel symbols are symmetric in the lower indices, so that's the same thing as gamma theta, theta r. That, it turns out, is equal to 1 over r. And the other Christoffel symbols, gamma r theta, is always the same as gamma r theta r, but in this case, it's equal to 0. All right, so now if we compute our covariant derivative using these components, Vr is 0, V theta is minus 1. And let's also repeat the general definition of the covariant derivative. This is partial alpha V mu plus gamma alpha beta mu V beta. In this case, since both of these components are constants, the derivatives must vanish. So now let's just start computing. We have, let's start with the RR component. Okay, we can ignore this term, so this is setting alpha equal to r and mu equal to r. We have gamma r, r beta, v beta. The only component of v that doesn't vanish is v theta, so this is minus gamma r, r theta, but gamma r, r theta was 0. Okay, we can also next compute del theta vr. Ignoring this term, we have gamma theta r beta v beta, but again, the only term that survives in the sum over beta is when beta is equal to theta, and then it's minus 1, so this is minus gamma r theta theta, but gamma r theta theta, we computed up here, is minus r, so with the extra minus sign we have r. The remaining components are del r v theta and del theta v theta. I won't go through the calculations of these, they're fairly straightforward. This is minus 1 over r, and this is 0. So these are the components of an operator. Del alpha v mu dx alpha outer product with by d by dx mu. And the only non-zero terms in the sums over alpha and mu are when one of those indices is theta and the other index is r. Right? So if alpha is theta and mu is r, then we have r times d x theta, or just d theta, outer product with d by dr. And from this non-zero component, we have minus 1 over r times the alpha index is r, so that's dr outer product with d by d theta. This is our result for the covariant derivative of the vector field v, and we carried out this calculation entirely in polar coordinates. Let me remind you, the result that we got in Cartesian coordinates was dy outer product with d by dx minus dx outer product d by dy. So the question is, are these the same? All right, of course the answer is yes, and we can see that explicitly by, for example, we can convert this expression in Cartesian coordinates into polar coordinates to find this result. How do we do that? Well, let's remind ourselves x is r cosine theta, y is r sine theta, so dx is cosine theta dr minus r sine theta d theta. Dy is sine theta dr plus r cosine theta d theta. And we also have the results that we've used a number of times. D by dx is cosine theta d by dr minus sine theta over r d by d theta. And d by dy is sine theta d by dr plus cosine theta over r d by d theta. All right, so if we put these results in here, well, let's put them in to this expression for our operator in Cartesian coordinates. What we have is del alpha v mu dx alpha cross with d by dx mu is equal to dy, that's sine theta dr plus r cosine theta d theta, outer product with d by dx, which is cosine theta d by dr minus sine theta over r d by d theta, minus dx, so that's cosine theta dr minus r sine theta d theta, outer product with d by dy, so that's sine theta d by dr plus cosine theta over r d by d theta. And now, if we look carefully, we should probably see some cancellations. For example, we have this term multiplying this term. We have a sine and a cosine, and that cancels with the minus sign here, the product of those two terms. Similarly, when we multiply this term and this term, we have an overall minus sign. The r's cancel. We have a cosine and a sine. And likewise, so that's these two terms. And when we multiply these two terms, we again get the sine and cosine. The r's cancel, but we have an overall plus because of the two minuses. So those terms multiplying each other all cancel. And now we have terms which are basically the cross terms, terms like dr outer product with d by d theta and d theta outer product with d by dr. Those are the only terms that are left. We have, let's start with this term times this term. We have minus sine squared theta over r, then d theta outer product with d by d theta. Let's look at the corresponding term down here. We have minus cosine squared over r, also dr outer product with d by d theta. All right, and the remaining terms are the terms in which we have d theta outer product with d by dr. So here we have r cosine squared. And from these two terms we have minus and minus gives plus. We have r times sine squared. And all of that's times d theta outer product with d by dr. So our result is, of course, using sine squared plus cosine squared is 1. We have minus 1 over r, dr outer product with d by d theta, plus r d theta outer product d by dr. Now comparing that to what we had before in polar coordinates, we have minus 1 over r, dr outer product with d by d theta, plus r d theta outer product with d by dr. Precisely the same result we have here. So you can see it doesn't matter whether we do this calculation in Cartesian coordinates or polar coordinates or any other system of coordinates we like. The results are the same. Let's review some of the math that we've learned in these lessons. So a vector is an operator that maps functions. Well, at each point it maps a function to a number, but if we have a vector field, then it maps function to a function. And we denote that if v is a vector field, then we denote that by v acting on some function f gives us a function. All right, a covector is an operator that maps a vector to a function. Again, I'm thinking of a covector field. Right, so if w is a covector, it acts on a vector to give a function. We also define the metric. And the metric maps two vectors or two vector fields to a function. And we denoted that by G acting on, say, V and W. And now our latest object is the covariant derivative. Which maps a vector to a vector. Now, I never actually introduced a notation for this, an abstract notation. Sometimes people would just call it del V. So del V acting on a vector, say t, gives us a vector. In terms of a coordinate basis, what I mean by del V is just del alpha V mu dx alpha outer product with d by dx mu. All right, so when del V acts on a vector like t, that's del alpha v mu d by dx alpha, and we insert this vector into this slot, and then the outer product symbol now is no longer really needed since this is just a function. In fact, the function this is just the alpha component of t. So what we have here is just t alpha del alpha v mu d by dx mu. So what this del v has done is mapped a vector t to a vector, and here we've expressed that vector in terms of components and basis vectors. Since this is a vector, we can act on it with a covector. So if w is a covector, we can let w act on del v of t, so that would be t alpha del alpha v mu, then w acts on this vector, and when w acts on that vector, it just gives the w mu component of this covector. So this is t alpha del alpha v mu times w mu. Okay, in fact, we can let a covector act on del v without del v acting on t. So consider the following expression. We have w acting on del v, so that's w acting on, let's expand this in a coordinate basis, del alpha v mu dx alpha outer product d by dx mu. So w acts on the vector, that's del alpha v mu dx alpha, and w acting on d by dx mu, which is just a function, so I don't need the outer product symbol anymore. And again, this is just the w sub mu component. This is del alpha v mu times w mu dx alpha. So of course what we're left with here is a covector, so it's something that can act on a vector. So the covariant derivative, del v equals del alpha v mu dx alpha outer product d by dx mu. This is an interesting object in that it can act on vectors and it can also be acted upon by covectors. It can act on a vector and at the same time it can be acted upon by a covector. So now we come to an important definition of tensors. All right, a type NM tensor is an object or an operator that can act on M vectors and be acted upon by N covectors. Okay, so if we let our tensor be called T, then in a coordinate basis it would have this structure. It would have, the components would have N upper indices and M lower indices. So this is mu1 through mu n, nu1 through nu m, then dx nu1 outer product up to dx nu m outer product d by dx mu1 up to d by dx mu n. So this is a type NM tensor. So it has M slots for vectors. Those are all these slots. So it can act on up to M vectors, and it has N factors of d by dx mu that can be acted upon by covectors. So it can be acted upon by up to N covectors. So this is a type NM tensor, and the N refers to the number of upper indices in the components, and the M refers to the number of lower indices in the components. Let's look at some examples. All right, a vector, which we can write in a coordinate basis this way. This is a type 1, 0 tensor. It has one upper index, and it can be acted upon by one covector. A covector, which we can of course write this way, is a type 0, 1 tensor. All right, it can act on one vector and it has one lower index. The metric we can write as g mu nu dx mu, and before we wrote it without the outer product symbol, but now we can be a little more sophisticated and put the outer product symbol in here. This is the metric. It can act on two vectors. It's a type 0, 2 tensor. Right? It has two lower indices. We can also define the inverse metric as a type 2, 0 tensor. That would be g upper mu nu d by dx mu outer product d by dx nu. That's type 2, 0. We also have defined the covariant derivative. That's del alpha v mu dx alpha outer product d by dx mu. That's a type 1, 1 tensor. Right? It has one upper and one lower index in its components. Another tensor that we've seen is the identity tensor. It's just the tensor whose components are the Kronecker deltas. So this is delta mu nu dx mu outer product d by dx nu. This is also a type 1-1 tensor. I'll introduce more tensors in later lectures, but for now I want to focus on this covariant derivative So this del operator acts on vectors to give a type 1-1 tensor. So it acts on a 1-0 tensor, that's a vector, to give a 1-1 tensor. The question is, how does this operator, del, act on other tensors? Let's remind ourselves of how we defined the covariant derivative acting on a vector. We had the x alpha coordinate line, and v is a vector field, so it's defined at every point along in the neighborhood of this coordinate line. And if this is the point P and this is the point Q, then we defined the covariant derivative in terms of the parallel transport of the vector from Q back to point P. So this is the parallel transported vector from Q, and then we subtract those two vectors. So that's del alpha v was the limit of the vector that sits at point Q parallel transported back to point P. Then we subtract from that the vector that sits at point P divided by the coordinate interval delta x alpha. Now let's ask ourselves how the covariant derivative should act on a function. All right, del alpha acting on some function f would be given by the limit of the function value at point Q transported back to point P minus the function value at point P divided by delta x alpha. But a function is just a value, it's just a number, so when we transport it from Q to P, it doesn't change it. So this would be the same thing as the limit of the value of f at Q minus the value of f at P divided by delta x alpha. So that's just symbolically the ordinary derivative of f in the direction x alpha. So this is just partial f with respect to x alpha, or we can also denote that by partial alpha f. So the covariant derivative acting on a function is just the ordinary derivative. Now let's let the covariant derivative act on the function wv, where w is a covector and v is a vector. Actually, these are vector and covector fields. So this is a function. In fact, we could write this in terms of components as w mu v mu. All right, so letting the covariant derivative act on w of v, this function, we know that it acting on a function, it just acts as an ordinary derivative. So that's partial alpha acting on wv, but wv can be written this way, so that's partial alpha w mu v mu. Now these are just ordinary functions, so we can use the product rule to write this as w mu partial alpha v mu plus partial alpha w mu times v mu. Let's just save this result for a moment and take a look at what we mean by this. What we mean is the limit of wv at the point Q parallel transported to the point P, and whatever that number is, we'll subtract from that wv at point P, divide by delta x alpha. All right, now we will assert that this number is the same as the number that we obtained by taking the covector at point Q and transporting it back to point P and letting that act on the vector that we obtained, that the vector at point Q transported back to point P. Okay, so now this is, of course, the covector at point P acting on the vector at point P. all of that divided by x alpha. Let's choose our vector field v to be parallel transported along the coordinate line. So in other words, I'm going to construct this vector field v along this coordinate line by starting with the vector at some point p, so this is the vector at point p, and parallel transporting everywhere along this line. So in particular at point q, here's the vector at point q, it's by definition parallel to the vector at point p. So when we parallel transport this vector q back to point p, we have the same vector as the vector that already sits at point P. All right, if we construct the vector field that way, then we can see here that this is just the vector that sits at point P. So we can write del alpha acting on W of V is the limit of the covector transported from point Q to point P acting on the vector at point P minus the covector at point P acting on the vector at point P, divided by delta x alpha. So if I just rewrite this in the following way, this is the covector transported from Q to P minus the covector at point P divided by delta x alpha acting on the vector at point P. This is just the covariant derivative of the covector W. And it's a covector itself. It acts on a vector V. So we can write the covariant derivative of WV as del alpha W. We can write this in terms of components. So this would be the muth component of this covector wired together with the muth component of this vector. All right, and the notation usually is to not write the parenthesis here, so we'll write this as del alpha W mu V mu. But remember, what this refers to is the covariant derivative of the covector W along the x alpha coordinate line, and we're looking at the muth component of that covector. Let's remind ourselves that we previously wrote this expression in this way. All right, so we can set this equal to W mu partial alpha V mu plus partial alpha W mu V mu. And furthermore, because V is parallel transported, we have del alpha V mu equals 0, which, writing this out explicitly, that tells us that partial alpha V mu plus Christoffel symbols, gamma alpha beta mu V beta, is equal to 0. So we can replace this with minus this. Putting this all together, we have from here del alpha W mu times V mu equals, this term is minus W mu gamma mu alpha beta V beta, and this term is partial alpha W mu V mu. Notice in this expression we have a repeated index beta that's being summed over, also a repeated index mu that's being summed over. So we can call those anything we like, and in particular what I'd like to do on this term is just swap the names mu and beta. So let's write this as minus W beta gamma beta alpha mu V mu. Then our last term is partial alpha W mu V mu. All right, written in this way, we have a common factor of V mu in each of these terms. Now I'd like to cancel this common factor, and I can do so because this vector is arbitrary. Remember, this is actually the vector at point P, so even though the vector field is not arbitrary, it's constructed by parallel transport, the vector at point P can be anything. So in order for this equality to hold, it must hold with the v mu's stripped away. So what we have then is the covariant derivative of the covector w, the muth component of that, is equal to, let me write this term first, ordinary derivative of the components w mu minus gamma alpha mu beta w beta. So this is our result for the covariant derivative acting on a covector. And just to remind you, the covariant derivative acting on a vector is given by a very similar formula. It starts with the ordinary derivative, then plus sign rather than minus, gamma alpha mu beta v beta. We can now use this same type of reasoning to determine how the covariant derivative acts on any type NM tensor. So an NM tensor T, what we would do is we would let this tensor act on vectors and be acted on covectors to form a function. And then we know how the covariant derivative acts on functions, and we also now know how it acts on both vectors and covectors. So by writing all that out, we can determine how the covariant derivative acts on the tensor T. The result is actually a fairly simple pattern. Del alpha acting on a type NM tensor has, the components have n superscript indices and m subscript indices. And this always starts with just the ordinary derivative. And then there are Christoffel symbol terms. For each one of the upper indices, we have a term that's similar to, that's just like the term that we have in the upper index for a vector. Right, so this would be gamma alpha beta mu1 t beta, then mu2 up to mu n, and the lower indices just stay the same. And the next term would be gamma alpha beta mu2 times t mu1 beta, and then mu2 up to mu n. And the lower indices stay the same, and so forth. So for each of the upper indices in T, we have a term in which we've replaced the upper index with a beta, and we've put that upper index onto the Christoffel symbol. Okay. Now for the lower indices, we have terms that are terms that are just like this one, follow the same pattern. So this would be gamma alpha nu1 beta t. The upper indices are going to stay the same, mu1 through mu n. And the lower indices, I'm going to swap the first one. And then this would be nu2 up to nu m. The next term we have gamma beta alpha nu2 t nu1, then beta, then nu2, and so forth up to nu m. So for each one of the lower indices, we have a term in which we've swapped the lower index for a beta and then put that lower index onto the Christoffel symbols. So this is the general result for any type NM tensor for the covariant derivative. Note that when we let the covariant derivative act on this type NM tensor, what we've constructed is a type NM plus 1 tensor. That tensor has these components. You'll notice there are now m plus 1 lower indices. That means there are m plus 1 slots in which we can insert a vector.